on additional science that we can do with LEM along these lines. Oops. I guess I have to do that. There we go. Okay, so one of the questions that we have to ask ourselves is when we're considering Milky Way science is how does it connect directly back to some of the larger science topics that LEM is going to address with regards to the intergalactic and circumgalactic medium. Well, we have to remember that we're occupying a unique place in the universe where we're embedded in this Milky Way galaxy, and many of the processes which we observe in our own galaxy are those same processes that are going to drive the chemistry and energetics in circum and intergalactic media of other galaxies. And many of these processes are actually driven by feedback from star forming regions, massive winds of stars, or even solar type stars, supernova and their remnants, and then taking one step farther back, outflows from galactic nuclei. And in this case, the Milky Way ecosystem, which it is an ecosystem, does provide a unique laboratory for understanding these drivers at scales from parsecs to kiloparsecs. And these are actually the subgrid physics scales, which are important for driving these large simulations, which have already been touched on. Along these lines, LEM is uniquely suited to probe the connection between stellar life cycles, these large scale outflows, and the chemistry of the Milky Way's circumgalactic medium. So I'm just going to talk about some of the topics that we've discussed in our working group and how it relates to this theme. And I'm going to start, of course, by talking about supernova remnants, which is something that's quite near and dear to me. What I'm showing here is a simulation of a core collapse supernova in the upper left-hand corner. This is about a half a second after core collapse, and this is the nickel distribution in the ejecta. Okay. And when you compare this to something like CAS-A, you see that this highly asymmetric explosion is actually imprinted by way of a highly asymmetric looking supernova remnant. This middle panel here, which is sort of occulted a little bit, is a CAS-A that's been smoothed to a LEM-like resolution, and it's only over the LEM band of, say, 0.1 to 2.1 keV. Now, I'll note that CAS-A is heavily absorbed, so we're losing a lot of that information from the soft X-rays. But if we look at other objects which aren't so absorbed, such as Magellanic Cloud objects or Cygnus Loop or Puppis-A, we will recover a lot of that soft X-ray emission. What we see is that the supernova remnant looks highly asymmetric, much like the explosion. And what this, when we look at something like this with LEM, especially with something with 2 eV resolution in the microcalorimeter, we're actually going to enable mapping of the velocity structure of the ejecta down to line of sight velocities of a few hundred kilometers per second at 800 eV. And this will occur at subparsec scales. So this is something that we do in the optical regularly. This is sort of spectral tomography. We don't do this in the X-ray because it's very difficult to do with something like a grading observation of a supernova remnant. Let's face it, supernova are not that bright in the X-rays for very long, so it's very difficult to do. But we do this in the optical, and I'll show an example of that and how we'll actually be able to do the same thing in the X-ray as well. But this 2 eV resolution, which LEM is going to afford us, will actually allow us to map both the red and the blue shifted components of the emission, and we can actually trace this directly back to asymmetries in the explosion. So we see this all the time in optical observations. This is up down in the center is a plot of the different nucleosynthetic burning products. We have oxygen emission, and then we'll have the products of explosive oxygen burning, notably sulfur and argon. And you can see that in this particular object, the products of the explosive oxygen burning are actually systematically slower than the oxygen. So this suggests that the burning that occurred during the explosion, the explosion itself was not well mixed. So the heavier elements are moving with a systematically slower velocity. So LEM is actually going to be able to make similar observations in X-rays, and we'll actually be able to measure line of sight of ejecta along different compositional layers. This is something which has not been done in the X-rays before. It's done with supernova, and only recently it's starting to be done with supernova remnants with various optical IFUs. So this is a very unique opportunity to trace the explosion physics in galactic and nearby supernova remnants. So along these lines, LEM will actually be able to survey a large population of the galactic and Magellanic Cloud population. The large field of view will mean that we can look at some of these larger objects and map them completely. You can see that in this plot here, I'm just showing what sort of the average velocities of the ejecta or the line of sight velocities in some cases, and what sort of energy resolution we'll need. And since we're expecting to have 2 eV resolution, what this suggests is that even near the rims of supernova remnants in the galaxy, we'll be able to measure the line of sight velocity of the ejecta across the entire or most of the LEM band. This will be useful because we'll be able to decompose that velocity from the thermal broadening and probe additional physics related to thermal heating of ejecta and equilibration between ions and electrons. Okay. So moving on to another topic, which is similarly related to supernova remnants, but may seem a little bit odd for an X-ray telescope, is the topic of dust and dust enrichment into the interstellar medium. We know from observations in the infrared and optical and other bands that supernova efficiently produce dust. One thing we don't know is how well that dust is mixed into the interstellar medium. The reason, of course, is because as the cold dust interacts with the shocks in the supernova and supernova remnant, much of that dust is destroyed. So there are questions about the efficiency of this dust destruction process. Now, there have been simulations that suggest that silicates with radii down to about a 1/4 micron can survive this sputtering process of the shock, while carbonaceous dust will survive down to much smaller radii. And this dust is what is effectively mixed into the interstellar medium. What does this have to do with LEM? Well, what will happen is when this dust is shocked by the reverse shock in the supernova remnant, you're left with neutral silicon, which will then, of course, produce a K-shell emission. And what I'm showing here is an EBIT spectrum for silicon K-shell emission, and it extends from around 1750 EV all the way up to 2000 EV. And this covers the LEM band. Now we know, if you've ever looked at an observation of a galactic supernova remnant, that really what this looks like in CCD resolution is maybe 1 or 1.5 lines. So you really can't decompose the emission from, say, the silicon, which arises from the dust, versus the atomic phase silicon, which is heated and gives you the helium-like state. So this will be something that's very unique to LEM, and it's unique in the sense that we'll be able to do this on scales of around 15 arc seconds across the whole remnant. So we'll be able to map the dust content in the X-rays across. Okay. Okay. All right. So moving on to a couple more topics that LEM will address related to the Milky Way and also to feedback. We have star formation is something that LEM will be able to investigate, and star formation and how that feeds back into the Milky Way's circumgalactic medium. This is a prototypical stellar nursery, the Orion Nebula. It's got massive stars in the trapezium with mechanical velocities in excess of 10 to the 36 ergs per second, mechanical luminosities in excess of 10 to the 36 ergs per second. We know that there's past supernova activity because there's a presence of radioactive aluminum. Now there's a cavity, a hot cavity with a luminosity of 10 to the 32 ergs per second. And observations have shown that some of this X-ray emitting gas actually funnels into the Eridanus superbubble, which is nearby. And what LEM will do is actually going to trace the feedback from this hot cavity into the superbubble and then out into the circumgalactic medium. So we'll be tracing the input of energy from stellar winds and other processes from these relatively small regions into a much larger environment. Okay, Akash had briefly discussed this earlier. We're planning to do or we're considering a partial or all-sky survey with LEM. What I'm showing up here in the upper right-hand corner is what that observation might look like. This is based on one of the simulations, and it's just been decomposed into various LEM energy bands. And I apologize, I don't know what the bands are. But we can also use the exquisite resolution microcalorimeter to measure the velocity of the material in the interstellar medium with an accuracy of around less than a half an EV at 600 EV. And this corresponds to plus or minus 200 kilometers per second. So what exactly would an all-sky survey allow us to do? Well, we could do shadow observations of molecular clouds, and this would allow us to separate local from circumgalactic medium emission. We can probe emission from that's coming from inside the Fermi bubbles and other galactic outflows. And lastly, we will be able to map absorption by oxygen 7 from the cosmic X-ray background in order to map the local hot bubble in high spectral detail. Okay, so lastly, I just want to talk briefly about a different form of feedback, which hasn't really been discussed, but sort of falls under the umbrella of observatory science. So when LEM is observing many of its key targets, it's going to be observing many background AGN that are just going to be caught in a 30 by 30 arc minute field. And these these AGN are going to inform us on the feedback from the AGN and the starburst into the host galaxy's environment. So what I'm showing up here in the upper right panel is a simulation of an AGN that LEM will observe. It's got non-thermal components from the accretion processes. It's got photoionization, and there's also thermal emission in this model, which accounts for the starburst activity. So when the AGN spectra is modeled and removed from this, what you're left behind and what LEM will observe is the velocity broadened outflow from the starburst, and we'll actually be able to measure the feedback from the AGN into its environment. Okay. So I'll just leave my summary slides up and I'll take questions at this time.
Okay, thank you. Okay, we have a question.
Please, you mentioned some diffuse black objects like thermal bubbles and supernova. I was wondering, have you thought about more compact things like pulsar wave nebulae? Do you LEM could resolve some of the thermal expansion?
The question was that you've been speaking about large-scale structures like Fermi bubbles and so on, and the question was whether you think LEM will be able to resolve more compact objects like, for example, pulsar wind nebulae and kind of emission, thermal emission from the shells around those.
Well, certainly LEM will be observing those types of supernova remnants which have embedded pulsar wind nebula, such as say G292 or 3C58, and we intend to be able to resolve the thermal emission around these objects. The LEM band doesn't extend into the hard X-rays where pulsar wind nebula are particularly bright. So we're currently exploring how we might be able to what we might learn from looking at the softer non-thermal X-rays from pulsar wind nebula. So.
Okay, thank you, Dan, again, and thank you to all the speakers. I want to thank everyone who came in person. We had quite a large crowd online as well, so thank you for joining. I hope you understand it was very hard for us to fit into this an hour and a half time to share the LEM mission with you. And please, if you have any more questions, feel free to approach any of us right now, at this meeting, online, later, whenever. We really want to hear from you. So go and enjoy your lunch or anything else that you have during the day. Thank you.